Hello, welcome to this video. So in this video I'm going to be talking about some of the challenges that come with learning physics and how the entangled web of connections that makes up physics demonstrates a beautiful tapestry underpinning our universe, but also how it makes learning physics sometimes super challenging. Because I know when many people are studying physics or hear words like quantum field theory or string theory, maybe the following emoji summarises how they feel. And I love physics, but I want to honour how difficult physics is, because it is very challenging. And so this video will be about exploring how to possibly navigate that challenge. So I'm going to begin by showing a fairly colourful mind map of a possible sequence of pathways through physics, and then I'll be talking about how to avoid getting stuck within cycles of physics, while saying this video is going to be slightly rambly in nature. However, hopefully the openness of the discussion will be a benefit, and well, it seems appropriate to have a slightly rambly video on a video which is about the very knotted tapestry that is the landscape of physics. So I've made a mind map. It is not the neatest mind map in the world. It is, though, hopefully fun. And I've tried to colour code things in, but I'll discuss it as I go through. So there are lots of ways you could draw the mind map of physics. Here is one that I've done. Now it's worth saying each of these topics you could do an entire course in at university. So these are very big chunky topics. And yet physics is full of kind of many interconnections between these ideas. So if we start with the more classical topics, and by classical I mean kind of like Newtonian physics, which I've tried to put into black as a colour, we have kind of classical mechanics, which is really the foundation of physics. It's the study of how things move, providing we're dealing with small velocities compared to the speed of light, and quantum phenomena are not obviously important. I say obviously because ultimately the ideas in classical mechanics, like Newton's second law, does have a origin in quantum mechanics. In the case of Newton's second law, if you take Schrödinger's equation and you go through the procedure to get to the Ehrenfest theorem, you end up with an expression which predicts, under the conditions in which classical physics operates, Newton's second law. So in classical mechanics, strictly one is dealing with an approximation of quantum mechanics. It's just the quantum mechanics is not manifestly or directly obvious. You need to study quantum mechanics in quite some depth before the links with the classical mechanics becomes clear. But you might think, okay, you've learned a bit of classical mechanics, where to go next? And immediately here there are quite a few different branches you could take. As we can see, I've drawn two branches out of classical mechanics, but you could draw far more. So after classical mechanics, I would personally recommend, although this is just my personal view, going either into a very mathematical direction, looking at advanced calculus. Now I put advanced calculus in black with a blue box around it because I couldn't decide whether to put it in the category of maths topics with strong links to pure maths, which I've colour coded as blue, or whether to put advanced calculus in the classical physics topic and so have it in black. So I kind of compromised and wrote advanced calculus in a blue box and wrote advanced calculus itself in black. And I wasn't sure whether to think of advanced calculus in the realms of classical physics or more pure maths, because advanced calculus was really pursued by mathematicians, and that led to real analysis and complex analysis, and in that form advanced calculus is very much an area of pure maths. But also physicists gave so much motivation, gave so much reasons for there to be a study of calculus in depth that advanced calculus has many links to physics, in that many times in physics you will have some integral, particularly when you're dealing with integrals combined with summations or partial derivatives, where you need more than general rules and you need to know maths in a bit more depth. So, is advanced calculus physics? Is advanced calculus an area of pure maths? It depends on how you're thinking about advanced calculus. So I didn't really know what category to put it in. But I would recommend, if you want the physics route, there's definitely a way of looking at advanced calculus that is more physicsy. If, however, you want to go down the maths route, and you really like the dynamics in classical mechanics, so you like thinking about things like initial conditions, you like things like vector calculus and Stokes theorem and all of that jazz, then I would recommend looking at classical field theory. And classical field theory is definitely heavily mathematical. It's a mathematical in-depth look at the kind of fields associated with the forces that classical mechanics deals with. So you can use classical field theory to look at Newtonian gravity in depth, to look at Gauss's law for electric fields in depth, so on and so forth. But also, if with classical mechanics you wanted to go to advanced calculus, it's worth saying that during classical mechanics, you're going to be touching on many of the other areas in this diagram. So classical mechanics has many, many branches. So it's actually physics is a lot more not to there making it look. But let's say, after classical mechanics you go to classical field theory. Well, where to go next? And here it really starts to get quite convoluted, because after classical field theory I would recommend either looking at electrodynamics, relativity, or variational calculus. Now, if you take the route of looking at electrodynamics, you'll be looking at essentially classical field theory ideas applied to Maxwell's equations. If you choose to go from classical field theory to relativity, you're going to start looking at concepts like simultaneity, and reference frames in more depth. And if you go from classical field theory to variational calculus, and I would recommend going to variational calculus if you want to stick with the very mathematical route, then you'll be starting to look at some physical ideas that arise in classical field theory, like Hamilton's principle of least action, in a great, in a great deal more depth, and generalise these ideas. And variational calculus is very good if you want to learn a particular form of quantum field theory known as the path integral approach to quantum field theory. However, and here's part of the difficulty with physics being so knotted, if you want to learn quantum field theory, you might have started with classical mechanics, gone to classical field theory, then learned variational calculus and think, well, yeah, you've spent possibly a whole year doing prerequisites, surely you're ready for quantum field theory, but no, you need to know something about quantum physics to understand how we're going to alter the ideas of classical fields to account for the uncertainty principle in quantum mechanics, or a generalised version of it. But to understand quantum physics, you need to have looked at statistical modelling in a lot of detail, because traditional interpretations of quantum mechanics are probabilistic in nature. So you might need to start studying some statistical physics before learning quantum physics. But let's say you were like, okay, I want to learn quantum field theory, but I realise I need to know quantum physics, and for that there's a prerequisite of statistical physics. So what can I do with statistical physics? Well, upon going on to statistical physics, you might get sidetracked and not get to quantum field theory for the next decade, because with statistical physics you can start understanding where principles like thermodynamic entropy and temperature come from, and there you're dealing with the link between statistical physics and thermal physics. And then you might come across articles in the news talking about black holes having thermodynamic properties and being examples of black bodies. But to understand, black holes, and therefore to study the thermodynamics of them, you need to know general relativity. So you might go from thermal physics to general relativity, but then you'll be like, oh, hang on, to understand general relativity, I need just standard relativity. Then on, after spending so long since looking at classical field theory where you began your journey, you might be like, oh, I've forgotten some classical field theory, so now I'm looking at relativity, I need to go back to classical field theory. And then the cycle might start again. And so you can get lost in this cycle and never get to quantum field theory through the path integral formulation. Or upon looking at statistical physics, you might get completely sidetracked and look at, quantum field theory from the canonical perspective. And that also requires an understanding of quantum physics. So, my discussion here might sound very knotted, but that's kind of the point I'm trying to make. Physics is an area where you can easily lose yourself in sidetracks, in rabbit holes, as I might call them. You can easily get, I wouldn't say trapped, but engrossed in a particular cycle that encompasses a very tiny aspect of physics. I think particularly if you're going to research, there's a huge danger of that happening. And the kind of entangled nature of physics, the risk of getting lost in sidetracks and stuck in cycles, makes getting a holistic approach to learning physics on the ground very difficult. It's very hard to learn physics in a holistic setting, and I have personal experience of the challenge with that, because I love physics, but as part of my passion for physics I try to learn physics in a very holistic manner. But that's difficult to do, and I think a lot of the time people say physics is hard to learn because it's abstract. That's correct. Because it's very mathematical. That is also correct. But I think the main difficulty with learning physics, in a holistic approach anyway, is how entangled and knotted these different branches of physics are. So, you know, I mean, it's really, really hard to get a good overview. And because it's so hard, I've actually not put arrows here because I want that to potentially help people see how to jump from one area to another in physics. However, everybody is starting physics potentially from a in-depth or particular fascination of a particular area, and that area will be different for each person. So I don't want to suggest you have to follow a particular route, but I would like to show the variety of routes, but also emphasise how, whilst the interlocking nature of physics creates this really harmonious, really rich nature to physics, it also makes learning physics really difficult. So if you're currently trying to learn physics and finding the vastness and entangled nature of it overwhelming, I wouldn't worry. I think that feeling is something anyone is going to experience who wants to gain a broad but detailed overview of physics. And that's also whilst I would, recommend many times to develop a broad overview, because physics is so entangled, it's helpful to have that for the same reasons. That is, since physics is so entangled, I would also say it is helpful to specialise in a particular area, just so you can have days where you're not getting semi-swamped by the entangled nature of the subject, which I think without specialisation in some area, at least for some days of the month, is going to be an inevitability. So that's some of the challenges with learning physics. Now here, to avoid this mind map becoming ridiculously complicated, I've avoided putting cycles here, but I think it might be good to talk about some of those cycles you can get lost in, to discuss a bit more about the potential danger of getting lost within a particular cycle, and how it's very easy to get lost in cycles. And I've come up with two cycles which I'm going to discuss. It's worth saying I came up with them within about a minute of thinking, and that implies that there were probably hundreds of cycles. But I'm sharing the two that first came to mind. Having seen the mind map, we're now going to go into a couple of cycles. Now it's worth saying my handwriting by this point definitely wasn't the neatest. However, I like to keep these kind of mind map things fun, if you like. So I stuck with the slightly wiggly at times writing. But anyway, here's one of the cycles I feel it's easy to get stuck in, and all of these topics are found within the mind map we just covered. So if you'd like to see what other areas of physics these topics are linked to, I would recommend jumping back to that mind map. But for the purpose of just the cycle, I'm just sticking with this tiny segments of the mind map. So we've got a cycle that links optics, classical field theory, and electrodynamics. And by cycle, I mean you could easily spend your whole physics career just looking at these three topics and kind of going around in a loop, um, without really branching out much. So, I mean, one of the reasons why it's easy to get lost in cycles is actually because physics is so broad. When you are stuck in a cycle of learning a particular group of ideas, you are still going to be making contact with other ideas, and that can make it kind of difficult to know that actually you've been doing the same three subjects for the past 10 years and are potentially missing out on a lot of other wonderful areas of physics. So, like optics deals with light, but when I say light, I really mean electromagnetic radiation. So if you're dealing with optics, you'll probably be at some point going beyond visible light telescopes and microscopy, and you might start thinking about how radio telescopes might be receiving signals from neutron stars. You might start thinking about how gamma ray photons are detected in PET scans and how that can help the medical sector. You could touch on a lot of range of things with optics. And optics itself falls under two categories, which is geometric optics, which is essentially looking at how light rays move, and then you have physical optics, which is looking at the ideas underpinning the movement of light rays. So in physical optics, you might be using Maxwell's equations to derive Snell's law, for example. And classical optics has a very strong link with classical field theory because physical optics makes use of Maxwell's equations, and Maxwell's equations are examples of classical fields. So after doing lots of optics, you might want to learn more about classical field theory potential broadly. And with classical field theory, you'll look at electric and magnetic fields, and that might lead you to look at how transformers work, and therefore, like the national grid. If you're interested in magnetic fields, you might again think further about a particular group of neutron stars called magnetars. You might also think about other things like magnons. You might start thinking about superconductivity. You might start thinking about magnetic domains. You might start thinking about spin. There's many routes you could go down with magnetism. And if you're particularly fascinated by electric and magnetic fields, you can look at electrodynamics, which kind of takes Maxwell's equations, but extends them far past just electromagnetic waves, and it looks at things like the motion of charged particles, and, for example, how light, as it transmits energy, can be thought of having a momentum associated with it, and how that momentum can lead to radiation pressure, which helps prevent the sun from collapsing. So you might start touching on main sequence stars and stellar evolution. So, as you can tell, even within the cycle, you are going to be touching and dealing with the fringes, the kind of outer regions of different topics. And that can make it hard to spot that you're in this cycle. But this isn't the only cycle that's easy to get trapped in. Here's another cycle. So this cycle is, if you like, the modern physics route with mixes of general relativity and quantum field theory. So in this cycle you might start with variational calculus, for example, particularly if you're coming from a maths background, and that looks at things like, if we've got a ball going down a slope, what needs to be the what needs to be the shape of the slope, slight tongue twister there, such that the ball crosses the slope in the shortest amount of time. Now obviously if the slope is vertical that's trivial, but what if the slope isn't allowed to be vertical? And that leads to the study of shapes, which can be described by hyperbolic trigonometric functions, so things like cosine, sine, and that kind of thing. And in variational calculus, hyperbolic trigonometric functions play a starring role. So if you've seen hyperbolic trigonometric functions in further maths and are wondering where to use them, variational calculus might be a thing worth studying. After looking at variational calculus, if you want to use it in the physics context, a brilliant area of physics in which to use variational calculus is quantum field theory, particularly the path integral formulation, allows one to see how the action, which is defined in terms of variational calculus, is minimized for classical systems, and why that isn't necessarily the case for quantum systems. And maybe after looking at quantum field theory, you want to have a broader understanding of field theory, and therefore considering fields that are classical. Now, classical field theory is traditionally associated with Maxwell's equations and electrodynamics, because Maxwell's equations are an example of a linear classical field theory. However, you can have other classical field theories that aren't linear. For example, general relativity is a classical field theory. It's just a non-linear classical field theory. So when looking at classical field theory, you might want to look at general relativity in depth, and therefore study things like black hole mergers, and that might lead you down to studying things like interferometry, and maybe quantum optics, because those things are useful for detecting gravitational waves which occur as a result of black hole mergers. So, this is another cycle where there are so many side things you touch on, it's easy to forget that you might actually be somewhat stuck on the cycle. And it's worth saying there is nothing wrong with focusing on a cycle of topics. And I think if people want to do that, they should be encouraged to do that. However, I think the danger is you might not want to get stuck within the cycle and yet be stuck in the cycle but just not know it. And it's worth saying with these cycles you can start anywhere within the cycle. For example, with the cycle involving optics, you might not start with looking at optics, you might start looking at classical field theory and yet get stuck in the cycle, just as somebody who is studying optics may get stuck in that same cycle. Or somebody studying optics might get stuck in a similar looking but slightly different cycle. So there are so many cycles within physics. It's you can't go, well, if I'm studying these topics very regularly, I am definitely stuck within a cycle. So it's hard to identify if you're stuck within a cycle. So, cycles make having a broad overview of physics rather difficult, and it also makes it hard to know where to start. Because, say, for example, you want to know general relativity. Well, do you start with quantum field theory or variational calculus? Or do you start with something that isn't in the cycle I've drawn, which involves classical field theory? Say you want to learn general relativity, you might, particularly if you're coming from a physics background rather than a mathematical background, you'll probably be looking at general relativity after having looked at special relativity. So maybe you want to look at special relativity first before looking at classical field theory and then delving deeply into general relativity. So, where do you start if you want to learn a particular topic? And the only thing I can really recommend is don't worry about prerequisites. And I know that might sound rather strange advice. I can't think of many cases where I've heard YouTubers or educators in general, or even just people casually chatting, suggesting that people don't worry about prerequisites. But I think in physics, really don't worry about prerequisites. And the reason I say that is because if you worry about prerequisites, you will find quickly that you're going to end up thinking you have to learn the entirety of the rest of physics before learning that topic. But you won't even be able to do that because to learn the entirety of the rest of physics, you have to know that topic properly in the first place. So essentially, don't worry about prerequisites. Simply because there's no practical way to really worry about them and yet still study physics. I would say studying physics is much like writing a story. Now, I love writing stories, and, my experience writing stories is much less than my experience doing physics, and even in physics I have far, far to go. But, it has sometimes happened where people have asked me, about my experience or means love of writing stories. My main credential when it comes to writing stories is just a love for the creativity of it. Sometimes I'm asked, I'm sure other people who write stories also get asked this, where do you start with a story? If you've got an idea for a story, where do you start? And my answer is always, well, start with that idea. And it doesn't matter whether that idea is the end of a story, where it's meant to be at the middle or beginning of a story, or whether it's a theme of a story, or an emotion, or a setting, or something that feels like it should be part of a story but you have no idea what the story is about yet. Just start with what you are passionate about or what you really want to write about. Now, the same thing is true for studying physics. If there's a topic you're really interested in, I would recommend gathering a collection of free resources. That involves making use of local libraries, potentially. It's also a good way to support local libraries, but there's tons of stuff online. You can also, probably purchase books as well, if you really want to, although there are a lot of free resources too. And after gathering a large collection of resources, start learning the subject, but be prepared that during each chapter probably, particularly if you're starting out in physics, this will happen less often the more you learn physics, but if you're just starting out, there's going to be something in that chapter which you don't really feel like you understand properly. And it's worth rereading to just check that you have understood the parts before it. But if you understood the parts before it but don't understand that thing, then look at the keywords that thing is mentioning, and then do your best to understand, I wouldn't say 100%, but 80% or the majority of the kind of core maths or physics around the idea. But if you can't do that, just learn a way of thinking about that idea that helps that part of the book make sense, and then return to the book. And so use a book on a topic, or a PDF, or an MIT open courseware. Use that as the main resource, but always be willing to branch out to learn about different areas or ideas as you're learning the subject you're trying to learn. And this freestyle approach to learning physics is always also a really good way to not get stuck into cycles. Now, the one slight caveat I would make is being confident with mathematics before going on to any advanced areas of physics. And by advanced, I mean if you pick up the book and you look at the maths, and I mean the equations. I don't mean the physical interpretation of them, but just the equations, and you're like, there's lots of symbols I haven't seen there before. I don't understand the algebra, or how to go from one step to another, and that keeps happening during a free resource. Then probably that resource is assuming mathematical knowledge that you may not yet possess. And a lot of modern physics does presume a lot of mathematics. Now, if it's just a little bit of mathematics you need to learn, I would say treat that little bit of mathematics as you would treat little bits of physics that you have to use sidetracks to learn. But if there's a lot of maths in the book you're really struggling with, I would recommend like seeing what type of symbols or ideas keep coming up in maths that confuse you, and then find a book or resource on that maths topic and focus on that resource before going back to the book. And the good thing with maths resources is because maths is so logically tight, it's actually a lot easier. Well, in terms of convolution complications, it's a lot easier to learn an area of maths than physics. Maths does come with its own maths does come with its own challenges. So I'm not saying that maths is easier to learn than physics, but it's easier to learn a topic in maths without getting lost in convolutions than it is in physics. Because maths is much less convoluted. There are so many links between concepts in maths, but because maths is very structured, it's much less convoluted than physics, whereas physics is incredibly convoluted. There's not really much we can do about it because that's the universe we live in. And that convolution brings richness to physics, but it also makes physics very hard to learn. And so I'm making this video as both a way to help people learn more physics who would like to, and to navigate through it somehow, either by perhaps making your own mind map, or maybe as a template using a mind map similar to mine. And, you know, maybe some of my suggestions on gathering lots of resources and on tackling the maths of physics before physics may help. But it's also worth saying that, you know, the entangled nature of the universe is part of what makes physics beautiful. So I think it is a delight that physics is like this. It's just a delight that one sees as a delight the further one goes in physics. You know, the more physics I do, the more delightful this entangled nature of physics seems, because it's much more easier to manage the entangled nature, and the tapestry is becoming ever richer. But it's worth saying, when I first tried learning advanced physics, and in this context I mean, you know, like higher education physics, the entangled nature of it was somewhat daunting. And somewhat is a dramatic understatement. But the more physics I've done, the easier it is to manage the entangled web, because I'm just now much more familiar with many aspects of physics than when I, first, walked into my university lecture theatres. Having said that, I have a huge way to go, and there are many aspects of physics I do not understand, and even if I was to live 1,000 years, I still feel I would scratch the surface of maybe 10% of physics, and that's being, I think, very optimistic. So physics is really broad, and I think everybody struggles with the broadness, but it is something that becomes easier to manage as time goes by. So hopefully this is motivational for anyone who currently feels maybe mildly lost within the web of our mathematical universe. But anyway, hope this video has been helpful. Hope you've got something out of it, and maybe enjoyed the break from so many equations that swamp physics textbooks and this channel. As much as I do love equations, it is important to take breaks from them as well. And so I hope you got something out of this video, and I'm wishing you a brilliant day ahead, and a brilliant time ahead exploring our wonderful universe. And I hope to see you for more physics, philosophy, and mathematics soon.